We learned about buffers in a previous lecture. What we're going to talk about now is the capacity of a buffer. You know, how much buffering can it actually do? Um, the definition of buffer capacity is the amount of H plus or OH minus that a buffer solution can absorb without a significant change in its pH. When we talk about significant change, we mean plus or minus 1 pH unit. So we don't want it to change more than 1 pH unit. It depends on the ratio between base and acid. That's going to affect the pH. Okay, if the amounts are equal, then we know that the pH is equal to the pKa, and we also can now say that if the concentrations are fairly big and the concentration of base and acid are equal, that's the best buffer you can make. Okay, that'll have the largest buffer capacity, and so it'll do a pretty good job of resisting pH. Okay. When you're making a buffer, you need to choose your weak acid and base carefully, because if you're making a buffer, usually you have a target pH in mind. You say, okay, I want to make a buffer that has close to biological pH. Biological pH is about 7.4. So if I want to make a buffer that has the pH of about 7.4, then I need to choose an acid whose Ka value, whose pKa value, is pretty close to 7.4. So then I can make a buffer and I can adjust the concentration of base and acid enough just to move the pH to 7.4 if I can't find an acid that's got an exactly right Ka value. So I have two solutions, C2H3O2, that's the acetate ion, to acetic acid, and this just shows you what happens to the pH if I start with a concentration where they're 1 molar to 1 molar, and then in B it's 1 molar to 0.1 molar. Okay, and then it can show you what happens to the pH if I change that. If the concentration of acid to base is base to acid rather, is rather large, then the percent of pH change is going to be rather large. Okay, so in solution B, there's such a small concentration of acetic acid compared to the base, the buffer capacity isn't very low. Right? It can't resist changes as well as it can in A. So here's an example. We have a buffered solution. It contains 0.25 molar ammonia, which the Kb value is there. You can do this with bases too. It's the same. It's treated the same way. And 0.40 molar in ammonium chloride. Calculate the pH of that solution. Okay. So NH3 plus water will give you NH4 plus and OH minus. We have an initial concentration of 0.25 molar for NH3, an initial concentration of 0.40 molar for NH4Cl. No hydroxide to begin with, but the change will happen as we would expect. We get new equilibrium concentrations. We put those into our Ka expression, or Kb expression, I should say. Okay, and we make the approximation, and we find that X is equal to 1.8 times 10 to the minus 5 hydroxide concentration. POH is 4.95, therefore pH is 14 minus 4.95, or 9.05. Okay, what if we had 0.020 moles of hydroxide to 500 milliliters, half a liter of this solution? All right, we've got a new ice table now. If we have half a liter of this solution, okay, that means that we have 0.200 moles, right? Volume times molarity equals moles. We have 0.020 moles of hydroxide initially, and then we have 0.125 moles of NH3 in this buffer solution. Now, what's going to happen? Well, all of the hydroxide is going to get used up by the NH4 plus, by that acid. So there's not going to be any hydroxide left at the end. This is just like our common ion problem before. Okay, our NH4 plus is going to go down by that 0.020 moles. Our NH3 is going to go up by 0.020 moles. So now we have new equilibrium concentrations of base and acid. Okay, some of that acid, NH4 plus, is now going to dissociate back into NH3. So I have to figure out what's going to happen there as far as how much H plus is this going to produce. So I set up my initial concentrations of NH4 and NH3 from the previous slide, and the changes as usual, what we would expect, giving new equilibrium concentrations. Okay, the ratio 1 times 10 to the minus 14th is Kw over 1.8 times 10 to the minus 5 is Kb. Kw divided by Kb is Ka. Remember, Ka times Kb is Kw. That's something that we learned in an earlier chapter. So now I have my new Ka value for NH4+. So if you're not given the Ka value for an acid, but you're given the Kb value for its conjugate base, then you can easily find the Ka value that you need. Okay, I plug in my expressions, I make the approximation, I find out that x is equal to 6.9 times 10 to the minus 10th. The approximation is definitely valid there. Concentration of H plus then is the negative log of that, or 9.16.